This is Aaron Newbill for the EE599 Project 4 assignment. Today I will be going over scaling up silicon photonic-based accelerators, the challenges and opportunities associated with this. Moving on to the abstract. The latest generation of CMOS multiply and accumulate operations have energy efficiencies from 10 to 100 femtojoules per operation. The speed of these, however, is limited to hundreds of megahertz. Optical and optoelectronic multiply accumulates can be realized at tens of gigahertz on today's silicon photonic integrated circuits. This leads to lower latencies and higher throughput, which can lead to higher efficiency in and boosting of other desirables. Moving on to the introduction section. Integrated optical modulation is more efficient than electronic switching for transmitting data over long distances. The Mach-Zehnder modulators are broadband and support complex modulation schemes. Micro-ring modulators have significantly smaller throughput, with a smaller footprint, and driving power consumption than digital CMOS technology. And the current generation of silicon photonics has matured with high volume shipments for data center transceivers. These Mach-Zehnder interferometers and micro-ring resonators are used as high-speed optical switches and filters. And silicon photonics can be used in computation in the analog domain, and through utilization of these Mach-Zehnder interferometers, modulators, micro-ring resonators, and modulators, these can be used for training accelerators in applications where convolution takes 80% of the total processing time, such as with machine learning and neuromorphic computing applications. Next is Section 2, the Mach-Zehnder modulator-based silicon photonic implementation. Starting with the system architecture, light from off-chip is coupled. This can be seen in Figure 1 down here. But to start, light from off-chip is coupled to the silicon photonic chip through an on-edge coupler by a polarization maintaining single-mode fiber. This is then split into parts depending on how many inputs there are to be modulated by an array of Mach-Zehnder interferometer modules. This is then fed into a weight transformation matrix, and this performs linear transformation for the input vector. As a result, this delivers outputs that are routed to photodetectors connected to electrical components, and this entire system utilizes transimpedance amplifiers as main amplifiers and sense amplifier-based comparators. Since single-value decomposition turns a real matrix into a product of unitary matrices in a diagonal matrix, as you can see over here, this it can realize this matrix topology. And the sequential product of these rotation matrices represents the sequential arrangement of linear transformation units in the overall matrix grid. This is practically implemented using a tunable beam splitter, which is comprised of a Mach-Zehnder interferometer with a phase shifter in at least one arm. It also possesses either an outer phase shifter or a tunable directional coupler, and this setup allows any arbitrary light distribution to be obtained by changing either the inner phase shifter or the outer phase shifter / tunable directional coupler. Moving on to Section B, the optical network budget. Photonic components were simulated in Cadence Spectra for 8x8 and 32x32 transformation matrix sizes. This was done to verify optical link budget analysis. The optical power of the laser was set to 0 decibels. This was done for estimating the power at the output terminals. Coupling loss into the silicon photonic chip introduced about 0.6 to 3 decibels of loss for the current coupling scheme used in this paper. Overall coupling loss from the laser to the silicon photonic is estimated at 1.6 decibels. Moving on, and furthermore, writing 3D waveguides into a photosensitive polymer demonstrated efficient interfacing between external sources to the silicon waveguide. For an input vector, light goes through splitters before modulation, and the insertion loss for these Mach-Zehnder modulations is approximated to be 1 decibel per millimeter. Next is the insertion loss. The insertion loss through a node is dependent on the excess loss for a cross statue. The excess loss for the cross state and the excess loss for the through state. Two phase shifters are connected using 3 decibel adiabatic directional couplers. And to study optical attenuation for the 8x8 Mach-Zehnder modulator, all inputs except the uppermost terminal were driven by V pi, which this creates a pi phase shift difference between the arms and nulls the outputs. The optical depth is equal to the number of inputs with a total number of the number of inputs times the number of inputs minus 1 divided by 2 optical crossings. The losses from the optical components in this multiplication matrix pose a limitation for scaling the network up. This is because highly attenuated optical intensities reach the outputs, which is undesirable. Next is section C, energy efficiency. The total electrical power dissipation of the network consists of the power consumed by the laser, the input modulators, and the thermal optic tuning of the matrix phase shifters. The analog front end, including there's the analog front end, which includes the photodetectors. As you can see, this is the optical link budget analysis for the Mach-Zehnder modulator-based matrices for each of their respective sizes. This is the stage within the optical network, and this is the optical power that was lost. One thing I do want to mention is that the use of a semiconductor optical amplifier will always degrade overall efficiency, and semiconductor optical amplifiers are necessary for regaining precision in the data. Power dissipated by the laser itself, the off-chip laser, is represented in terms of the laser's wall plug efficiency, the optical insertion loss from the SMF fiber, the fiber-to-chip coupling, the silicon waveguide loss, the input Mach-Zehnder loss, the weight phase shifter loss, the directional coupler loss, and the receiver's photodetective sensitivity. The total length of the waveguide was roughly approximated as the length spanning the optical depth of the matrix only, and the output sensitivity is solved based on the targeted resolution, and it's dependent on the total noise at the output front end, dark current and thermal noise, and laser relative intensity noise. Mach-Zehnder modulators consume power that scales linearly. The power consumed by drivers in analog front ends is about 2 picojoules per bit, and matrix rates are tuned using thermal optic phase shifters, and these depend on doped heaters, which dissipate around 20 milliwatts for a pi phase shift, and the efficiencies of these heaters can be improved through other heater materials, substrate undercut to improve the substrate undercut, and trenches to reduce thermal crosstalk. However, the use of heaters is not ideal because the issue with heaters is that heaters continuously drain power to operate, and there is thermal crosstalk. And as we'll get into later, the solutions listed prior, unfortunately, do have drawbacks in that they cause thermal isolation and self-heating. This exacerbates self-heating, and these silicon photonics are very sensitive to heat, especially with how small they are. Moving back to the document, the efficient optoelectronic receivers have efficiencies of 0.4 to 2.4 petajoules per bit. Higher analog front-end resolutions use linear transimpedance amplifiers along with analog to digital circuits to recover digital data. This is also what semiconductor optical amplifiers are for, recovering digital data as the light intensity decreases through modulation, phase shifting, and whatnot. Furthermore, high-speed linear transimpedance amplifiers have shown efficiencies as low as 0.6 petajoules per bit. Next is the high-speed serial inputs to the silicon photonic accelerator requires first in, first out, and multiplexers to interface data with DRAM. Power dissipation for these input and output circuits are accounted for within the calculations. And moving on to section D, the efficiency trade-off factors. The required laser power increases as a function related to the inputs as a result of the exponentially increasing optical losses in the Mach-Zehnder modulator accelerator. Total energy efficiency improves as n scales up due to the quadratic increase in the number of accelerated operations, and there is a scaling limit where optical losses grow significantly and the efficiency drops as a result. The maximum network scale is limited by the following factors. It's limited by the rated output optical power of the laser, and the signal to noise ratio required for any given signal resolution. Photodetectors with higher responsiveness improve the energy efficiency of the network, because if your photodetector is better at detecting light, you don't need as intensive a light. This can lead to less semiconductor optical amplifiers, which are energy intensive and unfortunately have a nonlinear gain, as we'll talk about later. Moving on, it compensates for the photodetectors with higher responsivities, also compensate for optical system loss. It relaxes the need to inject high optical power at the network input, and it improves overall efficiency. Laser optical intensity should be scaled by a factor of n to account for the splitting loss in a lossless network, and laser intensity can be as low as a single matrix input or the number of inputs times that amount. This is a conservative estimate for scaling the input power by n, and it may not be necessary with adaptable hidden layer resolutions. The heightened output resolution may be higher than needed by the analog front end to detect, and this specific principle allows the introduction of energy scaling versus loss of precision trade-off factor, where the maximum amount of energy savings is achieved when the reduction is tolerable at the optical output, which is the analog front end input. To put it simply, laser power can be traded for a loss of output resolution. The energy consumption for a digital multiply accumulate is estimated based on the energy consumed by multiplication and accumulation operators in register file access. And silicon photonics based on Mach-Zehnder modulators need to be scaled down to achieve higher resolutions. This unfortunately degrades energy efficiency, and the efficiencies for silicon photonic Mach-Zehnder multiply and accumulate operations were 3.5 to 17.5 times worse than digital CMOS. Mach-Zehnder modulator-based multiply accumulate operations are performed at 2 times the input times higher operating speed and lower latency and wait stationary compared to digital CMOS, and multiple clock cycles are needed for digital multipliers and adders and systolic arrays, and operating at around 10 times the lower clock speed further decreases throughput in comparison to optical implementations. The energy efficiency degrades at lower data rates as lower number of operations is conducted with respect to dissipated static power, and network size can be increased, however, making use of the signal noise ratio improvement at lower data rates. The next section is section 3, microring resonators based silicon photonic implementation. Starting with the system architecture, an outside laser is used to provide wavelengths. Implementing dot products through this has the advantage of equal path length for all outputs. The modulated input vector is split to be modulated by weight bank arrays. This through and drop transmission of the weight arrays are routed to balance photodetectors in a push-pull configuration for positive and negative polarities of the weights. Next, moving on to the optical network link budget. This is determined by the transmission insertion loss of the microring modulator for the input vector when resonance doesn't match the input wavelength. It is also determined by the transmission insertion loss of the microring resonator for the weight vector, and the out-of-band microring resonator insertion loss for the weight vector. Attenuation is introduced due to the splitting and cascading of the microrings, and which significantly degrades optical power. This leads to a maximum achievable matrix size of around 85 by 85 for binary networks. Next section is the energy efficiency. About 15 micrometers has been shown to be sufficient to avoid the thermal crosstalk of the heaters for tuning these microring resonators in a photonic switch implementation. The energy consumption of modulators and analog front ends increase linearly, and the overall energy efficiency improves with scaling. Microring modulators have a smaller footprint and lower input capacitance compared to their Mach-Zehnder counterparts and CMOS, and by extension CMOS. and there's a sizable reduction. This leads to a sizable reduction in driving power. Micro-ring modulators are much more sensitive to fabrication mismatch and thermal drift, however, and the scaling of power consumed by the heaters degrades the overall efficiency of this network. Next are the scaling limitations. Engineering the micro-ring resonator dimensions and coupling ratio compromises the quality factor. This degrades the channel spacings, and there is a limit to micro-ring resonator vector size. The next point is series coupling can reduce interchannel and intra-channel crosstalks. This maximizes the channel count and filter finesse. It has a higher footprint and a lower drop port transmission, but it requires extra tuning power. Contra-directional coupling in a micro-ring combines the wavelength selectivity with compact feature size, and this provides a free spectral range free response, which is good, and it requires extra heaters in the contra-directional coupling. The fourth section is research opportunities. There is research to be done in the optical loss reduction as passive alignment. Optical fibers can be accompanied using V-groove arrays. Optical signal attenuation can be compensated through semiconductor optical amplifiers. These can pre-amplify input signals and can be used in rate matrix element for weight magnitudes less than 1. It also improving analog front-end responsivity can improve performance, and it relaxes the need to increase laser power to compensate for the losses. Next is improving energy efficiency. Hybrid integration silicon photonic lasers can provide about 12.2% wall plug efficiency, while commercial continuous wave lasers suffer from low wall plug efficiency, around 1% to 10%. On-chip lasers can mitigate coupling losses, but these require wavelength stabilization and reflection cancellation. Thermal optic phase shifters dissipate high power coupling given their resistive nature. And techniques such as substrate removal and thermal isolation exacerbate self-heating. Going back to the point I made earlier, micro-ring resonators use heaters to tune themselves, but they are very sensitive to heat, and exacerbating self-heating and thermal isolation is not good, and as a result, further research should be done in removing these heaters as a tuning method. Alternatives have the potential to reduce tuning power overhead significantly, and these include nano-opto electromechanical systems, liquid crystal on silicon, and phase change materials. For Mach-Zehnder modulators, thermal optic phase shifters with insulation is the best for energy efficiency and network size, while nano-opto electrical mechanical system based phase shifters promise optimal reduction for large weight reuse factor. Micro-ring modulator implementations have similar results, but add in liquid crystal on silicon phase shifters. And next is section C, semiconductor optical amplifier cascadability. Semiconductor optical amplifiers are used to amplify optical signals over a given spectrum. These can be implemented off-chip or through hybrid integration, and these can increase the scale of the network. Semiconductor optical amplifiers are energy intensive with a few drawbacks: the noises produced from optical amplification, the ripples in the gain spectrum, and the amplification nonlinearity. The buildup of amplified spontaneous emission noise from the cascade degrades the signal-to-noise ratio, and the more semiconductor optical amplifiers there are in a network, the more amplified spontaneous emission noise, which is not good. The higher the spontaneous emission factor of the amplifier, the more amplified spontaneous emission noise as well. The signal-to-noise ratio is borderline unusable in non-semiconductor optical amplifierless networks, and semiconductor optical amplifiers can be added in the network before the signal-to-noise ratio degrades below the threshold. Signal-dependent noises, however, this amplifies these signal-dependent noises. Semiconductor optical amplifiers require introducing a 3,5 or a 2,4 compound semiconductor materials into the silicon photonic platform, but these are non-compliant with the standard silicon photonics foundry. Furthermore, narrow band filters can reduce the out-of-band noise, but this further reduces maximum channel count, which limits the scalability. Silicon optical amplifiers should deliver gains independent, ideally should deliver gains independent of input intensities. Highly efficient semiconductor optical amplifiers have the potential to increase network size, and improving the energy efficiency requires semiconductor optical amplifiers to have low injection count and high optical signal to noise ratio. Moving on to the conclusion. Silicon photonic implementations have relatively higher energy consumption and operate at lower bit resolutions. They cannot be scaled to large network sizes due to optical losses. The photonic multiply and accumulate operations have two distinct advantages. Optical multiply and accumulate operations can reach tens of gigahertz in terms of speed, and for tasks where memory access is not a limiter, optical implementation can reduce latency and improve energy efficiency at these high speeds. Multiplication operations can be intrinsically implemented in parallel, and the analog nature allows matrix operations to take place simultaneously. And the optical multiply accumulate implementations can increase throughput and improve the energy in the gigahertz speed range. The challenges of implementing these multiply and accumulate operations through silicon photonics is that there are the losses in optical circuits, which severely limit the size of the multiply accumulate networks that can be physically realized. Limitations of the silicon photonic multiply accumulate operations, accounting for the losses and power consumed by the laser and circuits that drive and control the optical circuits, accounting for the losses and power consumed by the laser and circuits that drive these control optical circuits, the energy efficiency is degraded. Analog multiply and accumulate operations have a maximum demonstrated resolution of 8.5 bits, and this is accurate for many inference tasks today. High throughput optical networks require accessing data at a high speed. This requires expensive hardware and a lot of energy. Next is the most low loss phase shifters have a reconfiguration speed from microseconds to milliseconds, which limits the use of photonic multiply accumulate operations to wait stationary systolic arrays. Higher levels of modulation require linear drives and transimpedance amplifiers. This challenges the design at a high speed and good energy efficiency. Well, this is challenging to design at a high speed and good energy efficiency. Packaging consideration and optics are far more challenging than packaging for electronic dies, and this is because of alignment accuracy and thermal management requirements. The mesh-like interconnections of Mach-Zehnder modulator-based implementations that extend the optical dynamic range at the analog front end place a trade-off between the laser power requirements and the output resolution. Mach-Zehnder modulators consume high electrical driver power, and Mach-Zehnder modulators cannot be made long due to the losses of their longer footprints. Microring resonator topologies provide better energy efficiencies. They have smaller footprint, meaning lower modulation energy consumption. Both Mach-Zehnder modulators and microring resonators experience major degradation to overall energy efficiencies. This is because of inefficiency in losses in lasers and phase shifters, insertion and excessive losses of the optical components, and the optical to electrical and electrical to optical conversion overhead. In order of magnitude higher operating speed and inherent parallelism in order of magnitude higher. Photonics can have an order of magnitude higher operating speed and inherent parallelism for multiplication of analog signals. This reduces delay and enhances throughput compared to digital CMOS. They have low energy tuning schemes that can significantly improve efficiency of photonic accelerators, and thermal tuning is efficient enough for mass production in case the other methods cannot be fabricated. The low voltage swing modulators with heterogeneous integration of polymers promise improvements in energy efficiency. Significant reduction in modulator and CMOS driver. These promise significant reduction in modulator and CMOS driver power consumption. Scaling silicon photonic accelerators to larger network sizes is limited, however, by the rated output optical power of the laser and signal to noise ratio required for a given signal resolution. This is because microring modulator networks can scale to larger values than their Mach-Zehnder modulator counterparts, and have lower losses with cascading microrings. Microring resonator networks are more, however, they are more sensitive to temperature, and until larger microring modulator-based networks are demonstrated, Mach-Zehnder modulator-based networks will continue to be favored. Heterogeneous integration of low-noise semiconductor optical amplifiers and silicon photonics can increase the network size, and and semiconductor optical amplifiers have high power consumption that degrades overall. But these semiconductor optical amplifiers have high power consumption that degrades overall efficiency. They have high responsivity and low noise avalanche photodetectors can aid in scaling the network sizes, and as well as reducing insertion losses on contributors can also help. And these contributors are directional couplers and phase shifters, and splitters are a significant limitation for scaling as well. This concludes the presentation 4. This concludes the presentation for the project 4 assignment. Thank you for your time.